Welcome back to the channel. Today's, I wouldn't call it a mini lecture, but it is a lecture. It's going to be covering a review of the 7 topics for the AP Environmental Science Test 2020. I've just given you a quick rundown on all of the topics. This will give you an opportunity to go through, make sure that you've got all of this nailed down, and then if necessary, after watching this, and you can go back and take additional notes if needed, do some additional research, and again, all of this should be documented on those resource pages that you're going to be using on your exam. Well, let's begin. So as we're getting ready to go through the year in review, remember we're going to be looking at the first 7 units, and they're going to necessarily be in order, but it's all going to be based around understanding how the natural world works, understanding what we as humans how we affect those natural systems, being able to accurately determine what an environmental problem is, and then developing and following some kind of sustainable relationship. Again, sustainability, Easter Island is a perfect example of not being sustainable. Remember, those individuals used every tree on the island. There is not a tree left. And in fact, those individuals turned into cannibals when they were found. There was no sacrifice to any further future generation. There wasn't any stewardship. They were not caring for something that was owned by all. They were only looking at the moment and looking at what the resources could give them immediately. So when you're thinking about sustainability, it also must follow a sound science. It has to be based on evidence, and it has to be able to be supported by the natural law. And so when you're considering sustainability, population must be included in that. Now, you have seen this graph before, the exponential growth rate of the human population. Again, we're looking at 7.3 billion people on this planet right now. And in the last 25 years, that population has grown by 2.5 billion. If you're looking into the future, we're looking at a population of 12 billion by the year 2050. When you have an increase in population, you have an increase in a need for resources. Now, just keep in mind that if I were to draw a circle around a certain area in Southeast Asia and India, I would actually be covering 70% of the world population in that small little circle on the globe. And so when you have, again, that increase of population numbers, you have an increasing need of resources. And one of the ways that we provide that resource is by growing the food. But that demand for food is destroying the soil, erosion, moisture, all of those things are happening. And then as we continue, we start to see global atmospheric changes. We actually see CO2 going into the atmosphere. We see those levels rising. Again, that process of global warming, the increase of the CO2 released through the burning of fossil fuels is like a blanket. It is trapping the infrared heat that would normally escape. In a normal balanced equation, the plants would be taking the CO2 out and then balancing that out and then storing that carbon. However, because of the excess CO2 being dispelled into the atmosphere, the plants in the ocean are being drastically affected. Also, we release chemicals, photo reactive chemicals that destroy ozone. And again, ozone is responsible for keeping us safe from UV radiation. Again, the loss of biodiversity can all be led back to habitat destruction. When you start to destroy the actual location that these species live in, you're reducing the amount of resources that are available, and therefore the populations cannot be supported. Again, we don't know the exact number of species lost because we don't know how many species there actually are. We discover new species almost every day. And so you must have a diverse cross section of biodiversity to have a strong and healthy ecosystem. Just a couple things to keep in mind. Most of the prescription drugs come from the rainforest, and as we destroy the rainforest, there may be species that we do not even know that we've wiped out. A couple of important people to know, again, Rachel Carson, Silent Spring, that was going back into DDT. Some more environmentalists that you should take note of. Again, you should recognize the tragedy of the commons. Again, that was the first lab we did. So if we're looking at the actual organization, again, if we're going from big to small, we're going universe to the biosphere, ecosphere, ecosystems, all the way down to the atom. But let's focus on the ecosystems. Again, when we're thinking of an ecosystem, ecosystem life is shaped by the abiotic factors. Think about all the abiotic factors that come into play: solar intensity, climate, weather, precipitation, nutrient levels, even to the point of topography. What is it close to? Is it close proximity to an ocean? Is it close proximity to a mountain chain, a desert? All of that's going to have great effects on the life in that ecosystem. And again, they're interacting. They are not just dependent upon each other, they are intradependent. As I push on any of those factors, it will have cascading effects throughout the entire ecosystem. You have to remember there are trophic relationships. Again, down there at the producers, those are always going to be your plants, and then those individuals that eat the plants, those would be your primary consumers. Your secondary consumers are always going to be carnivores. But again, as we go through that trophic level, each of those requirements is reduced by basically a factor of 90%. You have 100% of the energy available by the producers. It is using 90% for metabolism. 10% is then left for the primary consumer. And that just carries all the way up. As you're looking at energy requirements, well, that would also then support populations. If again, we're looking at the ecosystem as a whole, we need to be considering where is the biomass. The biomass is coming from the plants. The plants are all of your biomass, and the biomass gets its energy from the sun. Again, going back to the rule of tens, remember that as you move up the trophic pyramid, you are dropping a zero as you walk up that mountain with that energy that's available. Again, gross primary production is all of the energy that is produced by the plants. Net primary production is what is left after the cost of metabolism and all those things that we just talked about. Again, that rule of tens, what is available for the next level on the trophic pyramid. And in an ecosystem, you always have relationships, and those relationships come in lots of forms. Sometimes they are beneficial, that mutualistic relationship. You also have the commensalism, where one of them benefits, the other one doesn't even take notice. And then you have the predator-prey relationships, you have host-parasite, you have competition, both intra and interspecies. Remember, you're going to have them between individuals and between species for resources. And then make sure you really understand the difference between a habitat and a niche. Remember, a habitat is the wide range of the ecosystem. The niche is that special little place, that little nook and cranny that species inhabits. And think of again that pine tree that houses many species. They are not competing for food sources. They're all living in different areas, their own little niche. And again, limiting factors always going to be abiotic. These are going to be the things that decide what is your carrying capacity going to be. And if you start to exceed that, this is going to have those effects. And again, you have to also remember that when you combine effects, again, that synergistic effect, you're going to have a greater sum than you, by the two of them working together, than you would if one of them was alone. Again, the perfect example of that is the rate of pollution and then the incidence of disease. Again, think if all you had was pollution and no disease, you would only suffer the effects of the pollution. However, when you add the disease in, it makes it much worse. And so overall, how does an ecosystem work? Well, everything in the ecosystem has to be able to be fully recycled. Nothing is thrown away. And so everything, all matter, is then recycled through these three spheres: the lithosphere, the hydrosphere, and the atmosphere. And it is recycled biologically through the species living in the biosphere. Again, nothing is ever created, nothing is ever destroyed. There is no away when we throw something away. And so, another way to think about it is one species of food is another species poop. And so you have to have that entire chain where everything is being recycled all of the time. And again, primary energy source always going to be the sun. So let's talk about some quick things that you do need to have in the back of your pocket there. Remember what a calorie is. Remember the first laws of thermodynamics, the second law. You're never going to be able to get more out than you put in. You're never even going to be able to break even. Think about the chemistry that's in there. Your ionic bonds between metals and nonmetals, your covalent bonds, your sharing. And again, think of those hydrogen bonds. Those are the weakest of all. So photosynthesis, extremely inefficient. You may think this is a wonderful process. Well, it is, but it is only using about 1% of the energy from the sun that it is having access to. And so that's why we need lots and lots and lots of plants in order to do this process, because it is quite inefficient. And again, the reason it's doing photosynthesis is not for us. It is to create energy for cellular respiration. Okay, the cycles, the biogeochemical cycles that we've talked about. Make sure you understand the carbon cycle. Remember the carbon oxygen cycle together. Um, you have that whole system. Think about the nitrogen cycle, all of the steps that it takes, that most of the nitrogen on this planet is unusable. It has to be fixed into ammonium or a nitrate. And then we can create that through industrial processes. We can create it through lightning. We also create it through fossil fuels. Again, that's your nitrous oxide that's being pushed into the atmosphere. When you think of phosphorus, again, there's only two phases: no gas phase, only solid, only liquid. All of your man-made fertilizers contain organic phosphates. And so because phosphorus is a limiting factor in an aquatic system, this is going to cause rapid die-off, and we've talked about eutrophication. You may want to come back and get that chart, because that gives you a really nice way of thinking about how those biogeochemical cycles work. Again, carbon, hydrogen, oxygen, nitrogen, phosphorus, those are the main chemicals. And again, if you think of the different elements in Earth's crust, again, these are in order. You have oxygen, silica, aluminum, iron, calcium, sodium, phosphorus, and magnesium. And so there's a nice little mnemonic that you saw there. So if we're thinking about fires, they are beneficial in the long run. They are recycling all of those nutrients that are in those trees. However, when you have crown fires, again, those are when the entire tree catches on fire, the entire tree dies. And so you can have an entire change to an ecosystem because of something like a crown fire. And so the process of succession, again, when you have a bare land, there is a process for that to become an ecosystem. The primary succession is when you have that bare land, and then you have secondary succession. And the easy way to think of it is that rock has to be broken down first. Those pioneer species, those first plants to come in, are always going to be your lichens, your mosses, and your microbes. And they're going to be the ones that break down that rock material, turn that rock into soil, and then that soil then will support more and more hardy plants all the way up until you get to trees. And so we've talked about the energy flow, we've talked about the pyramid. Let's talk about evolutionary change real quickly. Make sure that you do understand DNA, chromosomes, genes, alleles. Remember, alleles are flavors of ice cream. Color of hair, black, brown, red. Those are all different flavors, all different alleles. Mutations are normal. They are a natural random event, and they can be caused just through replication of DNA. They could also be exposure to chemicals, exposure to ultraviolet radiation, um, and then radiation itself, such as uranium, things like that. Um, why do species change? Again, it's all going to be based on those abiotic factors. And so you do have a selective pressure, meaning that if I have a particular adaptation that makes me more competitive, makes me able to survive better, well, that is going to give me a competitive edge, and I'm going to be able to reproduce, and those traits are then passed down. Eventually, over long periods of time, the changes become big enough that we have what's called speciation, or the creation of two different species. Perfect example of this are the finches and the Galapagos. Those islands are very far apart, and so by having that separation over time, those individuals then became their own separate species, unable to breed. And it takes time for evolution. Yes, you can have some instantaneous, very quick explosions of life, but most of the time it's small little changes, long periods of time. So, human population, there's a lot of stuff that we've got to get here. We've talked about what the trends are, but primarily make sure you understand how to determine population growth rates. Again, you've got to think of what the crude birth rate is, what is the crude death rate, add in the immigration, take away the emigration. Again, that's per 1,000. And so when you have that, you're going to have a nice percentage of growth rate. Remember, R is the growth rate of a population. Here's a perfect example of how to do this. So population doubling. Remember, that's the rule of 70s, 70 divided by R. That gives you the time to doubling. We've talked about demographic transitioning, phase one, phase two, phase three, and phase four. Remember, we are in phase four. We are a modern industrial society, and there are reasons for the transitions. And again, if you really start to get into it, one of the greatest go-tos for this is women's rights. Once you start having women's rights, you start to see birth rates drop, you start to see death rates drop, you start to see fertility going lower, and all of a sudden that population becomes more and more stable. And so a couple of those rules, again, total fertility is all about the number of children born to the mother. Replacement is always going to be two. A developed country is going to have just a little bit more than two, having a solid population or stable. Developing countries will be above 2.5. Next, let's get into soil. Now, this is what we've just finished recently, so this should be fresh in your head. Again, some texture sizes. Sand is the biggest, clay is the smallest. And again, that makes sense because clay is pretty much impermeable to water. You've seen this soil classification pyramid. Again, you're looking at the three dimensions, sand, silt, and clay, and that's going to give you your best soil of loam. Now, you do have different classes of soil, again, based on, guess what, on the biome and the ecosystem that it's there. Little bit about water. We've talked about this as well. Again, most of Earth's water is stored in the oceans. Very, very, very little of it is available, accessible fresh water. And so when we start to think about that, even though we're not talking about water pollution, water is still considered part of land use. And so when you think of the use of fresh water, number one in the United States is for agriculture. Residential use, we use the most water to wash, clean, and flush. We use a lot of water to flush toilets. And in a typical person, 700 to 1,000 gallons a week. That's each of you doing that. We know about the different effects on the hydrological cycle. And again, that's just the process of heating up the water. You have evaporation, condensation, and then precipitation. But think of all the different ways that each of those is then affected. You've just finished, hopefully, the lectures on the Hadley cells and about atmospheric circulation, about global air circulation. And again, this is a pattern that's repeated all the way up north and south from the equator. And we can actually, by using these Hadley cells, do climate predictions. And then secondly, you also looked at the rain shadow here in the Central Valley of California. We are subject to this rain shadow. And then if you go a little bit further to the east, you run into an even greater rain shadow of the Sierra Nevadas, causing Death Valley and the Mojave Desert. We also have done a little bit of information about the Ogallala Aquifer and about how within probably the next 50 years, most of that water will be inaccessible or unusable. And it's all caused by, again, overpumping and unregulation. And again, this is not a lake stored underground, it is water stored in layers. Some examples of human interference: Mono Lake in Northern California. We took too much water out of the lake. It became very, very high concentrations of arsenic. You cannot even dip your little toe into that lake without having serious medical effects. And then we also know about Three Gorges Dam. We won't talk about that anymore. Food production. We use a lot of our land to grow food. And because we have to grow lots of food, we use lots of mechanical mechanisms to grow that food. Those are all solar powered, right? No, they're all running diesel, which means they're all putting fossil fuels emissions into the atmosphere. We also have to spray lots of pesticides and herbicides and fertilizers because we have to grow lots and lots and lots of food to support that population of 7.3 billion people and growing. Now, those are the things that we do. These are the effects. Because of the way we grow food, we have soil erosion. And as we have soil erosion, we have loss of fertility. Um, we also then have runoff that it goes into our lakes and streams. We're also putting those chemicals into the atmosphere. And so that's all affecting the ecosystem, causing biodiversity loss. You have degradation of habitats. We clear grasslands, we drain swamps and wetlands to grow food that we constantly then have to augment the soil. And then we wipe out genetic diversity by replacing lots and lots of different types of species that live there as far as the plant life with one species that lives there. Think of a cornfield, a soybean field, an almond orchard. Is there anything else growing there? Only corn, only soybeans, only almonds. And so we've talked about the Green Revolution, that this is not a good thing. It was not a great thing in terms of environmental. It was great as far as food production. It made the U.S. farmer the most productive human on the face of the earth, but there was a cost for that. It did not eliminate famine. Even though we have increased food production and we do make enough food to feed everyone, we still did not eliminate famine. The population rates are still increasing. It's costing more and more to produce the food. It has a severely negative environmental impact. Um, and what it's caused is a conglomeration of farms. The small farmer, the small 150, 200 acre farmer, is an endangered species. Most of these are conglomerates. And when you do not protect biodiversity and ecosystems, you have lots of things that can go wrong. And again, we've talked about some of those things. One of those is those endocrine disruptors, where we have all of these chemicals going into the water, and that is causing sexual reproductive problems in many animals that live in those aquatic environments. Energy. The next topic. Lots of information about energy. And so if you just think of US history, we started out with firewood, hydroelectric, and then we went to coal, and then we went to oil, and now we're with natural gas and oil and coal all together. So we use 30%, 37% of the world's produced oil. We get 4 out of every 10 barrels from foreign sources. Now, we did build a pipeline in Alaska, but that's not going to meet the ever increasing need of our our addiction to oil and the requirement that we're going to need to get that from foreign soils. Um, as we produce oil, we've talked about the local ecosystem damage. I'll give you one example, Deepwater Horizon. Um, Although it does create jobs and it is very energy dense as far as an energy source. Coal, on the other hand, we have tons and tons of coal available. In fact, we have one of the largest depositories of coal in the world. But getting it out of the ground is ugly. It must be mined. It produces tons and tons of fossil fuel emissions, lots of pollution. Natural gas, on the other hand, is much less environmental damaging fossil fuel. However, it is still going to have problems in the extraction method. Um, Although if we are just using natural gas, we are going to only be generating CO2 as a waste product. Again, electricity is not a primary energy source, it is a secondary energy source. We have to use something else to make electricity. And most of the ways we make electricity, boiling water, turning a turbine, that steam turns a turbine, and that turbine turns a generator. Even when I use nuclear power, I'm still using the same basic process of boiling water and then turning that water to steam, the steam turning a turbine. Now, a nice thing about nuclear power, no CO2 emissions, no greenhouse gas emissions. However, if things go wrong, this could get messy. Again, you could have the release of radioactive materials, and now we're talking about a whole nother ballgame. Again, none of our reactors are fusion reactors. That's what a star does, like our sun. We all have fission reactors, and the fuel we use is uranium 235. Most of the uranium found in nature is uranium 238. And so, in order to make fuel, that has to be purified. And so, that's very expensive. And again, we're throwing lots and lots of energy spinning that U-238 in centrifuges, refining it down to uranium 235 to use as a fuel rod. Again, this is a simple diagram of a nuclear power plant. You have your water, you have your control rods full of uranium, and then you have a turbine. Here's the problem with nuclear power. We don't have a good waste disposal system. Most of, or actually all of the spent fuel rods are still in the commercial nuclear facilities. We don't have them stored anywhere. And so we were going to put them into the ground in Yucca Mountain. That has never happened. It is a geologically unstable area, and there is a water table within close proximity. Here are some other accidents that have happened. Fukushima, the most recent. Chernobyl, also a complete meltdown. And then 3 Mile Island was a release of steam. Let's get into renewable energy. Again, not a fossil fuel, not nuclear. Renewable is sun, wind, geothermal, or falling water. So that would be rain, waterfalls, tides, all of that could be used as falling water. Two different kinds of solar. You have passive solar. Basically, think of a car sitting in the sun. You don't have a panel there, but your car is heating up. And so your lights, your windows would then trap the solar energy and it would then heat things up. Active solar is your actual photovoltaics, where you have the light rays striking, creating electricity. Seems like we're jumping around a little bit, but insecticides and pesticides, I just want to briefly mention an integrated pest management, or IPM. It's not going to just be chemicals. There's going to be several things in it. It's adjusting environmental conditions. It uses disease-resistant varieties. It brings in predator pests. But we know about DDT. It is a biomagnification and bioaccumulation in food chains. It's persistent, meaning it does not break down. And this was used all over the place as a way to kill pests. It is very effective. However, it accumulates all the way up the food chain. Um, pests bring disease, and so those must be controlled. Again, Lyme disease is from ticks, and there's been a huge outbreak of Lyme disease in the United States. Mosquitoes are vector for malaria for West Nile, and a lot of these diseases can be treated if we just had access to safe drinking water. That is almost always one of the vectors of disease is contaminated water sources. And so epidemiology is actually the study of the presence, distribution, and control of the disease. And then a couple terms that you may see would be morbidity, which would actually be the incidence, the number of people that get the disease in a population, and then mortality is the number of death in a population due to the disease. Next, we're going to move on to MSW, which is municipal solid waste. It's a pretty staggering number, the number of tons of municipal solid waste that are disposed of in the United States annually. And again, most of that waste is paper. And what do we do with it? We bury it in the ground. Now, some of that we do turn around and combust it and turn that into energy. But again, if we're burning something, what are we giving off? We're giving off greenhouse gases. And maybe the best solution to solid waste problems is actually to not make as much waste. What's crazy is almost 75%, more than 75% of municipal solid waste is recyclable. And so think about what could be done if we actually used a much more creative recycling program with our municipal solid waste. Think about how much less landfill space we would use. Now, there is some waste that we must be careful with, and those would be our hazardous wastes, such as the halogenated hydrocarbons. Again, we use these in pesticides. We use these to make plastics. They do not break down, and that's what we mean by them being persistent. They don't break down. They stay there for a very, very long period of time, doing their damage until basically the end days. These don't break down at all. And so when we have to dispose of these, we need to have a place to put these where they're not going to leach into the water supply, where they're not going to be burned and then go into the atmosphere, where they're not going to leach out of the dirt every time it rains. Another would be the chlorinated hydrocarbons. And again, these are synthetic organic compounds. Again, synthetic meaning man-made. We have dioxins, and again, we get that when you burn a PVC pipe. They're in medical waste, and we know the dioxins are linked to cancer. They are also an endocrine disruptor, causing all kinds of reproductive defects, both in the lower orders of animals. But again, this is something that is going to bioaccumulate and then biomagnify as it goes up the food chain. Again, these are hazardous wastes that we need to be very careful of when we're disposing them. Couple of examples of a waste site would be Love Canal in New York. The government decided it would be okay to go ahead and build housing over what was a toxic waste dump. The individuals living there became very, very ill, and it wasn't discovered until 1978 that there was a problem there. And so that was really the first national emergency in the US because of toxic waste, and that led to something called Superfund legislation. And so a Superfund the money is like a big pot, and so it comes from taxes, from chemical companies, from petroleum companies, and so they all pay into this. And then when there is a disaster, about 50% of that money is then spent on legal costs, and then the other 50% is used to clean up the mess. We should be able to go through this very quickly, as you guys were just assigned this as an assignment, the layers of the atmosphere. Again, the troposphere is where life is. It's about 80% nitrogen, 20% oxygen, and then tons and tons of trace elements. But again, as carbon dioxide increases, the greenhouse effect is going to increase. We also are creating tropospheric ozone. Again, ozone in the atmosphere is great. That's what protects us from ultraviolet B radiation. Ozone in the troposphere is photochemical smog. Now that leads us to air pollution. Um, the human costs are going to be very expensive over time, both the acute forms, the chronic forms, and the carcinogenic forms. Air pollution causes infrastructure damage. It destroys soils, and it does that through the simple system of acids and bases. If we have um, a higher than 7 on the pH scale, that's going to be basic. If we have lower than 7 on the pH scale, it's going to be acidic. Normal rainwater is a little bit below 7. Now it is running in the 6s and 5s. We also have indoor air pollutants, things like benzene, formaldehyde, radon, cigarette smoke. These are all coming from the chemicals we use to make our furniture, our rugs, our upholsteries. And so that's all off-gassing as we're sitting there. We've talked about the primary and secondary air pollutants. Again, primary is a direct product. Secondary is when it has a reaction in the atmosphere. You also have your particulate matter. And again, that's your PM. The size, the number is the size. Now, there are plenty of sources of air pollution. You have natural sources, but then you also have your anthropogenic, human caused. Almost all of them burning fossil fuels. Burning fossil fuels. Now, true, a forest fire is going to generate quite a bit of air pollution, but when I burn fossil fuels in a car, in a factory to make electricity, I'm doing nothing but generating air pollution. So, what is a solution? Reduce the emissions. And then we also can start to look at controlling the output. Can we start to scrub those exhaust fumes? Can we start to get rid of the excess going into the atmosphere? But again, even doing that is going to have a cost. If we coal wash, we're going to get rid of the sulfur, but where is the sulfur going to go? We have this waste ash that is then created that we have to dispose of. Okay, so I know that's a lot of stuff. The nice thing about having this on the video is you're going to be able to go back and review. And again, if there are certain areas that you think you might need to spend a little bit more time on, by all means, you've still got the textbook. Shoot me an email. I'll be happy to help you out with whatever I need to. We've got exactly 1 week until the AP exam. And again, I really feel strongly that you guys are going to do very well on this. So go through this video, again, rewind, replay, take notes, create your charts, get everything in place, ready to go. And as always, stay safe, stay home, and wash your hands.